For today, we'll be doing on strength of material as a course. First things first, let's define the concept of strength of material. What is strength of material? By definition, strength of material can be defined as the analysis of interaction between the externally applied load and the internal return forces of adhesion and cohesion. In our study of this course, we're going to be familiar with some terminologies, right? So let's discuss the basic terminologies in strength of material. They are as follows. Number one, rigidity. Rigidity. What is rigidity by definition? Rigidity can be defined as the ability of a material to resist deformation on the applied force / load, right? If I have a material such that, let me say for instance, let me use my phone as for example, for instance, as my load is, let's say this is my load, right? So this is a body. So if I put my marker on this body, actually this foam can never break or deform. Hence, this foam is what? A rigid body. But let me take for instance, if I have a bread, for instance, a bread, right? If I put a let's say a block on the bread, what happens there? The bread will deform, right? It will change shape. So that bread is called what? A non-rigid body, right? So the ability of material to resist deformation on the applied force / load is called what? Rigidity. Then there's the second terminology called elasticity, right? Elasticity. What is elasticity by definition? This can be defined as the ability of a body to regain its original shape and size after it has been distorted by an external force. That's the definition for rigidity. Sorry, elasticity. Let's look at the third terminologies called force. Force. Right? Force. Let's look at the definition of force. What is force? By definition, force can be defined as anything that tends to change the position of the body, either at rest or in motion. That is the definition of force as the third terminology. So let's look at the fourth terminology in strength of material, known as load. Load. All these terminologies are very important in our study of this course, right? So what is load by definition? Load can be defined in two cases, right? I can define load as the force that acts on a body. I can also define load as the force that acts on a structural member, usually at what? 90 degrees. So either of the two, you are correct. That's the definition for load. Let's look at the fifth terminologies called stress. Right? Stress. What is stress? By definition, stress can be defined as a force, right? That change. Okay. Stress. Okay, let me give you the short definition for stress. Stress can be defined as a force acting per unit area of deformation. Stress can be defined as a force acting per unit area of deformation. Stress is represented by a Greek symbol called sigma. B sigma, right? Sigma. So stress is represented by a Greek symbol called sigma. By my definition, I said stress is what? The force over area. Obviously, force is measured in what? In Newton. Area in what? Meter square. SI unit. My SI unit for stress is what? The Newton per meter square or Pascal. Any of the two, you're still correct. That's the fifth terminology. Stress is the force acting what? By unit area of deformation, and the SI unit is what? Newton per meter square or Pascal. So that's the fifth terminology. Let's look at the sixth terminology, the strength of material, known as strain. Right? So what is strain? By definition, strain is simply the ratio of deformation of a material to its original length. Strain is simply what? deformation of a material to its original length, right? So it's represented by a Greek symbol, right? This one, this is sigma, a Greek symbol called sigma. For this one, a Greek symbol called epsilon. And see that this is a Greek symbol called epsilon, right? So this is epsilon. So mathematically, from my definition, we said epsilon is equal to what? The deformation. Deformation of what? Of a material to its what? Original length. Of course, deformation is in what? In meter. Length is what? In also in meter. So meter cancels out meter. Hence, no SI unit. For what then? For strain. Observe please. Stress, meter per meter squared. Strain, no SI unit please. No SI unit. Let's look at the seventh terminologies called alright, stress, strain, deformation, right? Deformation. So what is deformation by definition? Deformation is simply the ability of a material to change its physical dimension, right? When a material changes shape and size, hence what are the order deformation has taken place, right? And we have two types of deformation, right? We have one, we call it elongation, and number two, we call it what? Contraction, right? Contraction or elongation. We said deformation is what? When a material changes the physical dimension, right? It's called deformation. Hence, deformation can be classified in two cases. Case one is what? Elongation. Case two is what? Alright, case one is what? Elongation. Case two is what? Contraction. So what is elongation? The ability for a material to increase its length is called what? Elongation. When a material increases its length, it's called elongation. Contraction is what? When the material decreases in length, it's called contraction. Right? So these are the basic terminologies in strength of material. Let's go to that concept called Oak's law. Right? Oak's law. Oak's law. So these are all the 7 basic terminologies in strength of material. So let's consider Oak's law. Alright. Let's consider Oak's law. Now, unlike the way you know it, Oak's law can be stated considering two things. Number one, considering force and extension, and number two, considering stress and strain. Let's discuss the first one, considering force and extension. Right? So put down. Oak's law can be stated. Oak's law, in terms of force and extension, says that the extension E of an elastic material is directly proportional to the force causing it. I said Oak's law can be stated in considering two things. The first one is what? Force and extension. So Oak's law, in terms of force and extension, says that the extension E of an elastic material is directly proportional to the force causing it. So mathematically, force is directly proportional to what? To extension E. Now listen please. From my definition I gave you, I mentioned extension before force. How come in my mathematical expression I have force before extension? For my definition, extension comes before force. Mathematically, my extension is meant to be here and force is meant to be here. How come force is here and extension is here? The reason there is that without force, there's never what? Extension. Look at my camera. My camera look at me. If my camera walks towards me and nobody's pulling it, I'll run away. Hence, so if there's no force applied to an object or a material, there's never what? An extension. So that's the reverse of the definition. So force comes before the extension. So in mathematics, when you have this sign, this is called what? The mathematics sign. So what comes in there? K. So F is equal to what then? KE. F is called the force, K is called stiffness of spring, and E is called extension. So this is the first case stating Hooke's law. Let's look at the second one, which is what then? We said considering two things. Force and extension are what then? Stress and strain. So let's look at strain and strain. Stress and strain. So let's test Hooke's law in terms of stress and strain. So Hooke's law in terms of stress and strain says that the strain of an elastic material is proportional to the stress causing it. Hence, stress is proportional to what? To strain. At this point, my constant term here will become what? Stress is equal to E strain. Now listen please. Here becomes K. Here becomes E. I said K is what is called what? The stiffness of spring. Why this is called Young's modulus base. So now, if I want to make my Young's modulus, so the formula, I'll have to divide by what? Strain divided by strain. Hence, strain cancel out strain, I'm left with what? Young's modulus. So hence, Young's modulus E is equal to what? Stress over strain. So if I'm to define Young's modulus, I can see that it's simply the what? The ratio of stress to strain. So that's the definition for non-modulus. So at this point, let's do some mathematical manipulations, right? Let's do some mathematical manipulation.
Pause it.
We established that non-modulus is equal to stress over strain. But we just said earlier that stress is equal to force over area. Also, we said that strain is equal to what then? Change in length over original length. If I substitute in this value here, I'll be having that Young's modulus E is equal to stress is what? Force over area. Right? So I have force over area this way. This is what? For stress. Over strain. We just said that what? This is what? Change in length over length. So change in length over length. If I apply my fraction concept here, I'll have that my Young's modulus is equal to F over A divided by what then? Change in length over length. Permits me to say that change in length is equal to E. Right? They are the same. So let me use E instead of change in length. At this point, I will have that Young's modulus E is equal to force over area. Force over area. This is what we convert to multiplication. So we got invert. Multiplied by, this is change in length over length. So you swap it. I'll have what the length over, because let's call this E over E. So if I multiply all through, I'll have E is equal to Fn over AE this way. Hence, at this point, make E the solid formula. I'll have E is equal to Fn over AE this way. So note that at this point, note that extension is equal to what then? Force multiplied by the length over area times Young's modulus. Alright, at this point, let's take an example. Let's take an example, a simpler example under tutor material before we move to some other concepts. Right? So put up this. Example. A square steel rod 40 mm by 40 mm. A square steel rod 40 mm by 40 mm is used to carry an axial load of 200 kN. A square steel rod 40 mm by 40 mm is used to carry an axial load of 200 kN. Full stop. Calculate the shortening in length of 100 mm. Calculate the shortening length of 100 mm, comma, if the Young's modulus is 4.28 times 10 to the power 8 kilonewton per meter square. Let me come again. I said a square steel rod 40 mm by 50 mm is used to carry an axial load of 200 kilonewton. Full stop. Calculate the shortening length of 100 mm if the Young's modulus is 4.28 times 10 to the power 8. Now here's the concept, please. Your first step in science is to what? List out what? Giving parameter. So what am I giving a question? Solution. My first task is what? I have a given parameter. So what am I giving a question? First is first. I said a square steel rod 40 mm by 40 mm. That 40 mm by 40 mm is actually dimension. Also, you can call it area. So let's call it area. Hence, area A is equal to what then? 40 mm by 40 mm. Please, it's not 40 m times 40 mm. It is by, please. By. So area is what? 40 mm by 40 mm. Is used to carry an axial load of 200 kilonewton. So I'm giving load, which is P, or you use F for it, any one of the two, is equal to what then? 200 kilonewton. Full stop. Calculate the shortening in length of 100 mm. So my length there, my length is L is equal to what then? 100 mm. So I'm going to calculate what? Shortening length, which is what? E, right? E. Please note that shortening length can be is also what? Deformation. And we said deformation represents two phases, either contraction or what? Elongation. At this point, because what the contraction, shortening length, so you're compressing that material. So I'm going to calculate shortening length. I'm given that the modulus E is equal to 4.28 times 10 to the power 8 kilonewton per meter square. Now listen, your first step in science is that list that parameter. Your next step is that are you converting? Obviously, I'm converting. For my concept here, sheet of material has one concept. Your modulus, any unit that your modulus is having, all this, you convert all these units to your modulus unit. Now at this point, I'm having kilonewton, no problem. I'm having meter, millimeter, there is problem. Hence, convert this to millimeter, meter to have uniformity of unit. So hence, if I convert this area to meter, so I'll have that area now, listen. Area is equal to what then? 0.04 meter multiplied by what? 0.04 meter as my area. Convert this one, length. If I convert length, is what? 0.1 meter. So hence I've converted my area and what? And length. So now listen. I have my load to be kilonewton, and I'm having here to be what? Kilonewton. If I choose to convert to newton, no problem, but it's not necessary, right? So since I'm having kilonewton, no problem. Meter, and meter, no stress. Now at this point, recall formula, right? At this point, I'll recall formula. I'm just calculating for what? Shortening length, extension E. So recall that we said E is equal to what? Fn over AE, right? So at this point, I'll plug in my values inside here, right? So extension E is now equal in value to F. Check. F is 200 kilonewton at this point. So I'll put what there? 200 multiplied by my length. Check. What length? 0.1 meter. So I'll put 0.1 meter at this point. All over area. Area is what there? These two people here, right? 0.04 multiply 0.04. I will have 1.6 times 10 to the power minus 3. If you multiply these two values, your area will be this, right? So multiplied by E is what? 4.28. I have 4.28 times 10 to the power 8 kilonewton. So this is my values here. So my extension E now is equal to if I multiply numerator, right? If I multiply these two, I'll have 20 all over. If I multiply my denominator, I'll have 6, 8, 4, 8, 1, 2, 3, 1, 2, 3, and 1. If I multiply these two, I'll have this. Hence, if I put my final answer, if I divide these two, I'll have that my extension E is equal to 2.92 times 10 to the power minus 5, right? In what? In meters. So here's my answer to this extension. Please, as I'm giving values, please also confirm your values, right? Because it's very important as part of this course. You punch calculator, please. Don't say you want to punch the exam when you start punching. Punch right now and observe your mistakes, right? So if I tell people to punch calculator, just this value, people will give me. Right, so people underrate punching calculator, right? So just observe, just imagine, right? At this stage, when you look at this stage, if you check some other courses, you solve some question for 3 hours. I'm not joking. 3 questions, you solve just a question for 3 hours. So imagine if I solve that question and your first 2 lines, you are making a mistake. How do you get the answer? So the concept is that whenever you are punching, ensure your punching was a correct value and also help them in punching. So this is my value for extension, right? So let's discuss the final concept under this stream of material and we'll call it a day. Type of stresses. Type of stress. Type of stresses. Type of stresses. Number 1, we have the tensile stress. Tensile stress. And number 2, we have compressive stress. Compressive stress. What is tensile stress by definition? What is tensile stress by definition? A tensile stress is a stress that tends to pull a material by increasing the length. Tensile stress is a stress that tends to pull the material by increasing its length. So I have diagram. This way. So draw the diagram. So this is a material. This is the original material. But when you pull it, it elongates, right? So this is for tensile stress. So tensile stress is stress that tends to pull a material by increasing its length. Let's discuss compressive stress. Compressive stress, by definition, is a kind of stress that tends to decrease. This increases, while this one decreases. So a compressive stress is a kind of stress that tends to reduce or decrease the length of a material. I have diagram. Compressive stress. I have diagram this way. Alright. Compressive stress is stress that tends to reduce or decrease the length of the material, which I have this. So those diagram. Alright, at this point, please observe 2 things. For my tensile stress, what happens? The length becomes increase while the height decreases. For compressive, the height becomes higher while the length becomes smaller. So observe this similarity between them. And note that for tensile, we are talking about elongation. Elongation. While for compressive, we are talking about contraction. Contraction, right? discussing, we're going to be dealing with some past questions on this course, right? So if you have found this class helpful, kindly click on the subscription button and like. Thank you. Welcome to